Welcome to Spring LIB.
This is the answer to Chapter 31, problem number 50 from the Smith Organic Chemistry textbook. And this problem asks us to provide the product for a number of reactions. And so looking at A, we can see that it's a vinyl type monomer that's going to be polymerized. Another clue there is that we have a peroxide type catalyst. And so we can just draw this as a typical polymerization, of which there are many in this chapter. And I'll just draw two subunits of it. So there we go. So it will polymerize at the double bond carbon, and there are the side chains. And so that's A. Again, it's just a typical polymerization. So for B, we're making a polypropylene from propylene from vinyl. And so we're told for B that we're using a Ziegler-Natta catalyst. And remember, the utility of the Ziegler-Natta catalyst is that it always provides isotactic side chains. So all the side chains are on the same side of the polymer. So we'll do three subunits here. And you could draw these. So they are methyl side chains. And so you could draw them like this, or you can make them all wedged or all dashed. And it doesn't matter which, as long as they all have that same configuration, because again, the Ziegler-Natta catalyst that we're told that we're using for this reaction specifically gives you that isotactic stereochemistry. So that's B. So then for C, we're going to have an anionic polymerization, and we know that because of the butyl lithium initiator that we're told to use. So we can go ahead and draw the product of that. So again, this is just going to be a typical polymerization. And I'm going to go ahead and draw this way. It may make it a little easier to see. And again, I'll just draw a dimer here. So two of these monomers linked together. But remember that the squiggly line bracket notation indicates that this polymer is continuing pretty much indefinitely in either direction. CH2, CH3, and then yeah, so I'll leave that at two subunits as well. So then D is going to be just another polymerization. So again, we'll use this same notation. And the side chains here are going to be a methyl and an ethyl group on each. So really, this is just another vinyl, another polypropylene, but with different side chains. And so I'll just draw two there as well. So that's D. So then looking at E, we have one of these epoxide-based polymerizations that we've seen previously in this chapter. And so the key to drawing this is just going to be to consider the way that the epoxides would open and remembering that that is how this particular monomer is going to polymerize. And so we have a 6-membered non-aromatic ring here. And then the linkages here are going to be carbon-oxygen bonds rather than carbon-carbon bonds. Okay, 6-membered ring there. And again, I will just stop at 2 there. But remember, the squiggly line bracket notation means really that it's continuing indefinitely. So then for F, so F is going to be a little bit different than E. So E, we only had epoxides. For F, we have 2 different monomers that are coming together to make a polymer. And so we do just need to show that. So the other thing to consider is that we have an excess of our epoxide. And so that's going to result in the epoxide units being the terminal pieces. And so we're actually going to put a bracket here to show that that's sort of a terminal piece. And that may make more sense once I draw the other bracket in. I'm just going to move that over to make sure I have enough space here. So then the actual units of the polymer are going to be these units here. So there's our ending bracket. And so this, what's contained inside the brackets is going to be the repeating unit of our polymer. And then again, the end pieces are going to be unopened epoxides. So there we go. All right. And so that's the answer to part F. So let me just start a new page here. So part G of this problem is different than the other parts that have come before. And indeed, the next 2, it looks like, are not forming polymers. They're hydrolyzing polymers back to the monomers. And so when we look at G, it's all ester linked. It's ester linkages. And we're told that we're treating it with hydroxide and water. And so we're just going to do a hydrolysis under basic conditions of those ester linkages. And so when we do so, what we end up with is a glycol. And we fix that. So it's a 4-carbon glycol. And this so it's basic condition. So it's not going to be a dicarboxylic acid. It's going to be a dicarboxylate. So it's this central aromatic ring. And then 2 carboxylates. So if this was under acidic conditions, it would be a dicarboxylic acid, but it's under basic conditions. So the correct way to draw this answer is to draw a dicarboxylate. And so that's what we have for G. H is going to be similar. It's a hydrolysis. The only difference is, of course, the pieces, and that H, the starting material, is an amide and not an ester. So this is a polyamide, not a polyester. But the principle is exactly the same. However, there's only one piece here, one monomer. So again, basic conditions. So we're going to end with a carboxylate ion on one end of this monomer. So there's our carboxylate ion, and then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. Did I count wrong? 2, 3, 4, 5, 6, 7, 8, 9. I did. Okay, so I apologize. 9 carbons after the carbonyl carbons. So 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons, 10 including the carbonyl carbon, and then a primary amine. And so that's the answer for H. Again, found just by hydrolyzing the amide bonds and seeing what that gives you. So then for I, we're back to forming polymers. And so we're forming a polyamide. And right, so we're going to be forming amide linkages. So it's going to look like this. So here's our first amide linkage. Second amide linkage. And then here's the other piece. So this is made from 2 different monomers. So they're going to alternate. So we've drawn our first monomer, our second monomer that I'm drawing now is the diol with a 6-membered non-aromatic ring. So that's there. And that is one subunit of this polymer. So two different monomers joined by amide linkages. Right. Okay. And then for J, J is so for J, we are forming a polyester. So, or pardon me, a polycarbonate. So this is a diol that we're starting with and treating that with phosgene. And so that's going to end up giving us just subunits of diol linked by carbonates, by just single carbon carbonates. And so to draw that, that's going to look like this. And we have 1, 2, 3, 4, so 4 carbon diol. And so that right there is a single unit. We could draw a second unit. Oops. So there we go. There's 2 subunits of our polymer. Again, it's a polycarbonate linked by carbonates. And J is the last part of this problem. And so taken together, this is the answer to chapter 31, problem number 50.